Okay, well, thanks, Terry. Thanks very much. I'm here today in place of Dennis Andrusik, who is the Deputy Associate Administrator for the Science Mission Directorate. When we first conceived of this workshop with Terry, we engaged Dr. Zerbuchen, the AA, and he was enthusiastic. We were hoping he could attend himself, but even when we first had these discussions back in April, we knew that he wouldn't attend because of budget briefings today at headquarters. Dennis, unfortunately, couldn't attend because Thomas had a death in the family and had to return to Switzerland. So I'm filling in for Dennis today, and I spoke to him briefly before coming out, and he thought, given that we had a large number of people not from within NASA, to start off with an overview of SMD would be helpful. And then to talk a little bit about the direction that Thomas is really trying to take SMD in terms of new technology. All right. Okay. So as many of you know, the directorate is comprised of 4 divisions: or heliophysics, earth science, planetary science, and astrophysics. And we try to coordinate the technology investments where we can in terms of cross-cutting technologies across the 4 divisions. But it's an integrated program that enables our science. By the numbers, we're a $5 billion organization which has over 100 spacecraft missions in play. We have $600 million invested in research and analysis. 10,000 scientists are funded through these programs, and many of those are competitively awarded. Our technology programs are over $400 million in annual investments, and we have a variety of investments also in suborbital platforms that not only perform outstanding science, but are important tools for validating and testing new technologies. This is a depiction of our current active fleet from the 4 divisions. This is a depiction of what's currently in the portfolio, and we can add, this is 24 more that are currently in formulation. So this is a golden era, really, for NASA science. We've never had this large number of missions before, and despite, we complain about budget issues all the time, it's worth, I think, taking a look at what's been accomplished and what's being accomplished now. This is really a great time to be part of NASA science. The main goals in our directorate are discovering the secrets of the universe, searching for life elsewhere, and safeguarding and improving life on Earth. And when you think about that, embedded in our directorate are most likely 2 of the great discoveries of the century: discovery of life in the solar system, discovery of a second Earth outside of the solar system, and then protecting the home planet, which is critical for, there's nothing more important than that. Tackling the problems of understanding what's causing the climate to change, and then in the next decade looking at most likely climate mitigation, these strategies with our Earth science data sets. This will be critical. And then just some eye candy from a recent mission. Many of you may have seen this. The flyover with Juno over the south pole of Jupiter. An amazing shot of the ammonia clouds. This is from the microwave radiometer that was on board Juno. And we learned the depth, the penetration of the ammonia in the southern, at the South Pole. All kinds of new science from these missions. So looking at just a couple of others in the fleet and in development, Mars 2020, our next generation of science instruments on the rover. We also have discoveries from Cassini, the discovery of hydrogen in the plumes that are coming off of the moon. Hubble detected the presence of plumes on the equator of Europa. So these are strong candidates for looking for life elsewhere in the solar system. And then outside of the solar system, the results from Kepler, the discovery of new planets. We've identified what's known as a habitable zone, or considered to be a habitable zone. We put Venus, Earth, and Mars for comparison. These planets are quite close to what we would consider a habitable zone. Of course, that's debatable. I think if you were looking at our solar system from afar, you might consider Venus and Mars to be in the habitable zone, but Mars is not habitable, and Venus is a hellscape of sorts. So it's not always clear what that means. But the discovery of these planets is certainly remarkable. And then more recently, with the Spitzer telescope, the discovery of 7 planets in the TRAPPIST system, which you probably heard, which was on the news last month. And then on Earth, we have a new instrument flying on board GOES-16, which is the lightning mapper, which is useful for predictions of thunderstorms and all kinds of applications for hazard detection and applied sciences. Okay, and then space weather as well. This is not an artist's rendition. This is actually a photograph taken from the International Space Station showing an aurora and the problems that it can cause with our power grids. In addition to those types of hazards, we're also, for planetary defense, we're looking at identifying near-Earth objects and those that might be of hazard to Earth. This was the recent, the 2013 event in Russia, and then this is a map of all the fireball events that have occurred since 1988, and you can see there's quite a few. The one in Russia being a much larger event, but still we've identified quite a few new near-Earth objects. So planetary defense will continue to be an important part of our research. Okay, so that's a little bit about what we do in SMD. When Dr. Zurbuchen arrived in October, he placed a special emphasis for our directorate to focus on advancing technology. And the role of technological innovation he sees as being important in all aspects of innovation, whether it's breakthrough, game-changing, incremental, or disruptive. And so this is kind of a theme that I'd like to emphasize for today, is that we're trying to go from a good posture where we are to good to great, so to speak. So the way he describes it is lean forward. Look at everything we're doing and how can we make it more innovative? How can we make it better? With the goal of improving science, creating new capabilities. So just some examples, breakthrough innovation. You could look at the SWAT mission, Earth Science Mission, which will be the first to have swath measurements of terrestrial water heights. Before they were just point measurements. But this mission design concept enables us to do much more with the Ka-band interferometer. This was a technology investment that occurred over a 10-year period by the Earth Science Technology Office. Game-changing innovation, an example is deep space optical communications. The fact that we'll have the ability to have much higher data rates in deep space will alter the missions, what the missions will be able to accomplish. We're flying an instance of DSOC on one of our planetary missions, on the Psyche mission. And this will be a way of retiring the risk and enabling the technology to be available for future missions. And then disruptive innovations, the Cygnus mission, which is performing radio occultation for examining ocean surface winds. This mission launched last year and has been very successful. It's a low-cost method of obtaining the ocean surface winds. Previously, we would have launched a scatterometer, but this, using very low-cost components, we were able to achieve a mission with a constellation of 8 low Earth orbiting spacecraft. And then a big emphasis in the directorate is on the ability for small satellites and CUBESATS to perform quality science. We achieved a tipping point where the instruments could be, many of the instruments could be miniaturized to fit on these small platforms, greatly reducing the cost, potentially reducing the cost for many of the missions. A lot of the new science will require constellations of spacecraft, so it requires a change in our investment strategy and technology to look at not only the instruments, but also the platform technology, which our partners in the Space Technology Mission Directorate have been investing in for several years. It's important for us in SMD to articulate our requirements to STMD so that there's a convergence of the instrument technology and the platform technology to enable these new missions. In October, I was asked by Dr. Zurbuchen to identify 4 areas where he felt we needed more investment in technology, areas that not necessarily were the most important areas, but areas that were perhaps neglected. And I identified 4, integrated photonics, which are essential for many of our sensors, enabling our next generation science missions. The small satellite technologies that I just described, and then autonomous systems was on the list. And he agreed that this was an area where we really didn't have focused programs, and we really didn't have a lot of strong mission requirements. And that's one reason we're here today. High-end computing, where we're at a point where Moore's law is at a plateau, and our ability to improve our performance of our models, of our engineering tools is hitting a wall. So we're going to have to do something different, and we'll be looking at that. And then Thomas added to the list big data and deep learning. He doesn't believe that we're pulling all the information out of the data stores from our science missions that we could be. He doesn't believe that we have a good investment strategy in big data and deep learning. So this is an area, and again, Ames is strong in this area, and it's something that we're going to be looking at. And then the problem of infusing the technologies. Many of you have heard of the term the Valley of Death. We have 13 technology programs in SMD. STMD has almost a dozen programs themselves. We're very good at making investments in the TRL 2 to 6 range, but then there's a problem. Those technologies, it's very difficult to get those infused into missions. We tend to be risk adverse. In order to fly new instruments, the unwritten rule is they have to have already flown. So we're not going to get very far if that's actually true. The way we've been implementing this in the past is by investing in our technology programs. And again, in SMD, it's mostly in science instruments in the TRL 3 to 5 range. We use our suborbital platforms and ground validation to do a lot of the risk assessment, to do to prepare it for TRL-6, which is required for infusion to a mission. And then the hope is that the missions will then use those technologies. But in the past, again, we have this valley of death with that right arrow there. So to address this, we're being more proactive with our partners in STMD, with the game-changing program and their technology demonstration mission program specifically. We're engaging them on a regular basis to go through their list of investments, and for the projects which are ending, we are proactively selecting them to be infused on our missions, to be offered up as technology demonstrations or technology infusions. And in addition to that, we're starting with our AO schedule, and we're working with STMD to identify technology topics for our future AOs, so going the other direction. So this started about 6 months ago, and I think this will be a good example of how we can address the valley of death issue that is, I think, plagued some of our missions. And then finally, rideshare opportunities. For all of the future SMD missions, we're planning to fly ESPA rings, and there will be opportunities to fly missions of opportunities with small satellites, ESPA-class satellites, and CUBESATs. And this will be very important for retiring risk of future instruments and platform technologies. So the goal then is to raise the bar on scientific discovery. All of this is really to, again, this theme of good to great, to take a good science program and make it much better. We have to identify the key technologies with high mission impact and fly them into space. And we get a lot of concerns when we have this discussion about the TMC, the process by which the missions are evaluated for risk. We're working directly with TMC to address that issue, and I think they understand what Dr. Zabukin is trying to accomplish, and I don't think that that's going to be an obstacle at all. So the takeaway here is really that technology is critical to the future of SMD and its missions. We're focusing on investments and pathways as strategic elements of our programs, and we are actively developing new flight opportunities for technologies as part of all of our AOs. And another problem that we have to solve is assessing the performance of our technology programs. We don't really have a lot of good metrics. The one metric that we've used in the past has been mission infusion, but we don't have really enough missions to use that as a sole metric. So we're looking at different metrics. Jacqueline Lemoyne is here, and she's had a lot of progress in that area, so we're going to be looking at a lot of her ideas. So that's really it. The message is really we want to push the technology forward. We want to make the missions bolder and more capable, and with the goal of improving the science. In the case of autonomy, like Terry said, the issue is really we don't have a strategy in SMD. The reason we don't have a strategy is because many of the mission concepts are not including advanced autonomy in their descriptions. And this could be, a chicken and an egg problem. We did this with optical communications. For the Earth science missions, we had no requirement for optical communications because they weren't designed for optical communications. But we could do a lot more. So we have to kind of break that cycle today. And that's why we wanted to have the scientists here with the technologists to have the conversation. The scientists need to think about, taking the current ideas for the missions, and if we had advanced autonomy, how could they be made better? And for the technologists who are here, you need to tell the scientists, hey, you can do this, you can't do that, this is what state of the art is today, this is where we think state-of-the-art will be 10 years from now. And finally, I think for the program managers at headquarters, I don't think, who are just some of the greatest people in the world, very good at what they do, but they don't have a lot of background in autonomy. And so an education for our program executives, I think, would be helpful, and it would help those individuals make informed decisions. So thank you very much.
So those of you who have not been here before or were not here during the week, this is the magic box that you can ask questions. In theory, there's a microphone embedded, so don't take this and try to bash your neighbor over the head with it. But it is, in some sense, throwable. So if you've got questions, raise your hand, and I will attempt to throw this to you, or at least pass it to you. So any questions for Mike?
Only at Ames.
Only at Ames. Who wants the magic box? Wake up. Jeremy, of course, Jeremy.
Good throw.
So thanks for a great talk, Mike. Let me ask, just from your perspective, so if from where you sit, if you're a scientist, why are you afraid of autonomy? Why don't you trust it? Why don't you want to use it?
I have no idea. I don't know. Maybe I suspect the capabilities.
Why do you assume that we're afraid of autonomy?
Most of the scientists I talk to don't want anything to do with it, so prove me wrong.
Sorry, I was holding too many. I do. That's all I have to say.
Great, let's talk.
Okay.
So let me ask a question while you've got the box there. Are there scientists who perhaps are concerned that if they proposed advanced autonomy in a mission that it would be rejected because of high risk?
I'm getting a nod over here, so I'm guessing that's true.
Is that a concern you have?
It is now, I guess, but I haven't been afraid of it though. Maybe because my husband works in autonomy and robotics, and so I see it and I see these advances that really blow my mind. It seems silly to not be incorporating that, actually.
Okay. It would be interesting to know how many of the scientists in the audience are concerned about proposal risk.
Try to throw it all the way across the room.
Thanks, Terry. Jack Burns, University of Colorado. You talked about disruptive technology. Autonomy is potentially one of those, and that was part of the theme of my talk yesterday at the end of the survey meeting, and it's something we talked about during the transition team as well. I was a part of the NASA transition team. But implementing disruptive technology within the system the way it is right now, particularly TMC reviews that the Science Mission Directorate holds, including going all the way down to Explorer missions, Discovery class missions, there's an intrinsic risk aversion that prevents such disruptive technologies from really being approved and going forward. There needs, and I've talked to Thomas about this, there needs to be a culture change also in the way NASA does its review panels. Until we do that, such exciting things like autonomous systems just simply aren't going to be selected for missions.
Totally agree.
I'm Peter Hughes, Goddard's Chief Technologist. I want to dispel the notion that we haven't done some autonomous missions. I will offer that we haven't done fully autonomous missions, and we can increase autonomy on missions, but we have examples throughout the agency at JPL and in Goddard, and I think Ames even has examples that some functions are autonomous. I know for Goddard's missions, the SWIFT spacecraft, when we detected a gamma ray burst, we made a real-time assessment whether it was worth the risk to re-slew the spacecraft. So that's one example, and it's not a backpatting. It's just that when we know what the function is we're going to get out of that, what the risk is involved, I think the scientists and the program managers are willing to accept that. I think we as an autonomy group had to identify what that capability is, what they're going to get out of it, what that trait is, and not just label it as a fully autonomous mission. I don't think they're going to accept that. So during the course of this workshop, I challenge us, come to better terms what we mean by autonomy, identifying the technology or for the functional areas we want to focus on, give good examples where it's successful and truly enabling, and cherry pick a few areas and a few missions that we could demonstrate why this feature, why this capability is absolutely critical for next generation missions.
So just a comment, Peter. I would state that the Mars rovers, both the current and the 2020 rover that's planned, is not using anywhere close to state-of-the-art with autonomy, and those missions could probably be made more capable. And then for Europa, for surface operations, I don't even think we can execute those missions that we want to do without really pushing the bar forward on autonomous systems.
I think it's necessary for us to identify where we've done it and where it's been successful, so we can still keep building this path forward to what we can do even more.
Yep.
I would say it might be worth actually maybe more properly defining autonomy, because it sounds like it means that the system is really going to actually be working all by itself without any input, and certainly scientists at least don't want to let go of that. But I know that that's not what autonomy means, at least to computer scientists and probably to engineers as well. I mean, even though it would, ideally, it's not actually how it's working in practice.
So that's why we have the real autonomy experts here, and hopefully they can help us with that. In fact, when we talked about this workshop, the use of the word autonomy they complained about.
So unfortunately, Isa, I'm going to cut you off before you even get started, but hold that thought. We have purposely planned this day to have a lot of opportunity for discussion, and so you can discuss and debate that, but I wanted to stop there because that was actually a perfect segue to the next talk, so we can get the slides up.